Hello again, and we are going to be working more on our physical science with our chemical reactions. So today, I want to talk to you a little bit about why it's important for us to balance chemical equations and how to go about balancing them. So the first thing I want us to remember is that the reason we balance is that we follow the law of conservation of mass. The law of conservation of mass says that the mass of the reactants must equal the mass of the products. Remember that the mass of the reactants are the reactants that we're using. What are we putting together to make a product? A prime example of this would be making a s'more or s'mores. I would take 2 crackers, a CQ. I would take 1 marshmallow, 3 squares of chocolate, and I get a s'more. And so we could see we have 2 crackers, 1 marshmallow, 3 chocolate squares, and we get 1 s'more, which looks like a very complicated chemical equation. If I look at that, I see that on my s'more right here, there are 3 squares of chocolate, 2 crackers, and 1 marshmallow. If I add up all these together, I should get 1 s'more. Even though there's 1 of these, I need 2 of those, 1 of those, and 3 of those. So how do we go about it and why? Well, I'm going to give you an example that I find very important in my classroom. In my classroom, we use a thing called Bunsen burners, and Bunsen burners burn natural gas. Natural gas is 1 carbon atom with 4 hydrogen. The name of this, another name for this, is methane, and the chemical formula is CH4. Now, in order for it to burn, I need to add oxygen. So I'm going to add oxygen. Remember, oxygen is diatomic, so it's O2. And I'm going to get carbon dioxide, 1 carbon and 2 oxygens, plus a water, which is 1 oxygen and 2 hydrogens. Now, looking at this, if I'm going to say that I'm going to balance it and follow the law of conservation of mass, I'm going to count and see what I have. In this side, starting right away from the beginning, I have 4 hydrogens. If I look on my product side, I only have 2 hydrogens. Now, the kicker is I can't add hydrogens over here. I have to add another product. So now I have 2 waters. But when I have 2 waters, I change something else. I have my 4 hydrogen on this side. That's the same as this side. I have my 1 carbon over here with my carbon dioxide and 1 carbon here with my methane. But if I count my oxygens, I have my red Lego bricks. I have 1, 2, 3, 4. On this side, I only have 2. So what would I have to add? Well, I'd have to add another oxygen, of course. So to balance this, that means I need 1 methane, 2 oxygen, I get 1 carbon dioxide, and 2 water. Now, obviously, I don't use my Lego bricks for all of these equations. I use another method. It's kind of a little bit of algebra, kind of a little counting that we're going to use to balance our equations. So if you would please look in your Google Classroom, and you're going to find a practice sheet in there called Balancing Equations. Go figure, huh? All right. And it looks sort of like this. Okay. So what I'm looking at, if you recall from the Legos, is that I wanted the colors of Legos and the size of Legos to match on the reactant side and on the product side. So I do the same thing here. I make a squiggle here that's like a barrier, like a fence. I put these here for the plus ones. And then I see what do I have in, what atoms do I have in here for my reactants? I have an iron. I have a hydrogen, a sulfur, and an oxygen. Iron, hydrogen, sulfur, and oxygen. I should have the same things over on the other side too. I was thinking that wasn't very balanced, so I was going to balance it for you. And if you look, I do. I have an iron, I have a hydrogen, I have a sulfur, and I have an oxygen. So now the goal is to count how many we have. In this column, I'm going to kind of put a little dotted line here. In this column right here, I want to count how many irons I have. Well, I have 1 iron. And then in this column, I'm going to show I have 2 hydrogen, 1 sulfur, and 4 oxygen. Let's go through that. I have 2 hydrogen, 1 sulfur, even though there's not a number there, it's understood to be 1, and 4 oxygen. Let's look on the reactant side. There was a 2 behind there, so I have 2. Now this becomes interesting. Like I said over here, this is like 1 sulfur, but I have it in parentheses. So I really have 3. 3 times 1. So I have 3 sulfur. 3 times 4 is oxygen. Let's do that one more time. Do you understand? This is 2, because there's a 2 on there. This is in parentheses, just like in mathematics. So I'm going to take the 3 times the 1, I get 3, and 3 times the 4, I get 12. And then over here, I see I have 2 hydrogen. Now when I balance equations, the thing that I look for is probably the most complicated one. I consider this one and this one the most complicated because they have the most elements in them. I look at it and I'm thinking, okay, this has sulfur and it has oxygen together in both of these. I'm going to determine something. What do I take this number times? What do I multiply this number by to get 3? And you would say 3. So I put a 3 in the box or in the line, and I take that 3 times 2 is 6, 3 times 1 is 3, 3 times 4 is 12. So if I look at this, I have 3 sulfurs here, 3 sulfurs there, 12 oxygens here, and 12 there. So those are balanced. Then I go ahead and go, I have 6 here and 2 here. 2 is a smaller number. Does 2 go into 6? Yes, so what times 2 would make 6? That would be 3. 3 times 2 is 6. So now they match. My hydrogens match. I go up to my iron. There's 2 here and there's 1 here. This is the smaller one. Can I take a number times this to get the 2? Yes, I can take it times 2. I put a 2 here. 2 times 1 is 2. So now I see that they all have the same amount and my equation is now balanced. I'm sure you're asking me, what about this one right here? Because I did not have to change anything, I did not have to multiply times anything, I don't write anything there. I could write a 1 right here. But 1 times 2 is 2, and 1 times 3 is 3, and 1 times 12 is 12. Just like in algebra, the 1 is understood. Let's try another one. To save paper, I have a tendency just to fold this over and start again, because sometimes it gets a little wonky. All right, let's look at number 3. Again, I go through it. I make my barrier between my reactants and my products. I show where my addition signs are, and I'm going to list the elements in the reactant side. I have a K, I have an O, and I have an H. I already have the H and O and a P. I should have the same thing over here if I wrote my equation correctly, and it looks like I did. So I have, these are my elements. I'm going to count how many potassiums I have in this particular substance. Again, these are understood to have 1, so I have 1, 1, and 1. Because these are all understood to be 1 in the subscripts. And the second one, I have 3, 1, and 4. 3 hydrogen, 1 phosphorus, and 4 oxygen. And the next one, I have 3 potassium, 1 phosphorus, and 4 hydrogen. I'm sorry, 4 oxygen. In the water, I have 2 hydrogen and 1 oxygen. So I look at this and think, something is not right. Here I have 4 hydrogens because I would add, this means add these together. I have 4 hydrogens. Here I only have 2. Here's 1 and 1, so that looks good. Hydrogens do not. Potassiums don't either. So what am I going to do? Again, I look at the most complicated to see if that can help me out. All right, with this one, I'm going to look at these two, my potassium right here, and I see that I have 3 there. The 1 is smaller. Can I take 1, because this is potassium, can I take 1 to make 3? What do I take it times? 3. So I place a 3 in there. 3 times 1 is 3. 3 times 1 is 3. 3 times 1 is 3. So now my potassiums match. But it sure looks like I made a mess out of the rest of the stuff, didn't it? Okay, so I have a 3 and a 4 here, and a 4 and a 1. I have 6 hydrogen here. 3 plus 3 is 6, so I have 6 hydrogen, and I have 2 hydrogen here. Oh, if this is 6 and this is 2, can I take the 2 times anything to get 6? And you would say yes, 3. So I'm going to take 3 times 1 is 3. 3 times 2 is 6. Okay, my phosphoruses match, and this is 6 and that's 6, and I made those match. 3 plus 4 is 7, and 4 plus 3 is 7. So therefore I have a balanced equation. I'm going to show you one that's a little bit tricky. So let's look at that one now. It's number 5. Getting my paper ready. Number 5. And the reason I say it's tricky is because the oxygen is split. It does some kind of funny things here that we're going to talk about. In the previous balanced equations, have you noticed that every coefficient is a whole number? And that's true. You can't have half of an atom. So we always have to have whole numbers for coefficients. So let's see what happens here. We have an N, an H, and an O. In this particular substance, I have 1 nitrogen and 3 hydrogen. In this one, I have 2 oxygen. In this substance, I have 1 nitrogen and 1 oxygen. And good old water, I have 2 hydrogens and 1 oxygen. So I look and say, hey, my nitrogens balance. That's cool. But my hydrogens don't. Notice it's a 3 and a 2. That makes it very difficult because I can't go 1.5. I can't do stuff like that. So I decide, what do 2 and 3 go into? Well, 2 and 3 both go into 6. So what do I take this times to get 6? And you would say 2. Again, 2 times 1 is 2. 2 times 3 is 6. So over here to get 6, I would take it times a 3. 3 times 2 is 6. 3 times 1 is 3. Okay? Now I have a 2 nitrogen here, so I would put a 2 here, correct? 2, 2. Yes? So now my nitrogens match, my hydrogen, let's go to the oxygens. I have 5 here and 2 there. Can I take 2 times some whole number to get 5? No. To get 5, I would have to go 2 times 2.5 to get 5. Well, I told you we can't do decimals or fractions as our coefficients. But I do know that 2.5 tells me, because this is like a half, if I would take everything of these times 2, it would balance out. So I would take because this is a half right here, I would take all my coefficients times 2. 4, 5, 4, 6. That means my reaction, my balanced equation, actually would look like 4 NH3s plus 5 O2s yield 4 NOs plus 6 H2O. That was a lot of work for that one, wasn't it? Hopefully I don't give you too many of those. Would you like to do one more? And then you can start your assignment. Let's do one more. I don't know which one we should pick. I'm trying to see here what I can do here with my camera. And I bet you're looking at the paper and going, oh, that number 9 looks tough. So let's try number 9. Everyone see number 9 on their paper? As a NH4, 3, PO4. Yeah, it looks like it could be a lot of work, doesn't it? So I put my paper down to match this out. And kids say, do I have to do it this way? No. You can count in your head. I'm sure some of you are seeing a pattern, and some of them you'll see a pattern and you'll go, yeah, I kind of get this. I can do this a little shorthand. And that's okay. But this way, I know that it works every single time. So that's why I use it. Again, same process. I have a nitrogen. I'm not going to skip spaces this time. Hydrogen, phosphorus, and oxygen. A lead, Pb. I already have N down. I already have 3. Okay, I have all that down. So these are my elements that I'm using. Let's make sure. An NHPO, a Pb, and an NO. Yep, I have them all written down. So let's go through how I'm going to count this. Remember this 3 out here, just like in algebra, it's like 3 times what's ever in here. So if this is a 1, this would be 3. 3 times 4 is 12. We have 1 phosphorus and 4 oxygen. This one, I have 1 lead. Okay, how many nitrogen? If you said 4, you're correct. And 4 times 3 is 12 oxygen. So on this side, if you look at it, I have 7 nitrogen, 12 hydrogen, 1 phosphorus, 4 plus 12 is 16 oxygen, and 1 lead. Let's go to this side and count. We have 3 lead. How many phosphorus? If you said 4, you're correct. And 4 times 4 is 16 oxygen. Oh, 16 oxygen match. Okay, how about this side? NH4NO3, I have 1. Oh, no, 2, don't I? I have 2 nitrogen. I have 4 hydrogen. And I have 3 oxygen. As you can see, I don't have anything that matches, do I? So my job is to start matching it. And how to do that? What can I do? Well, I'll be honest. They all look very complicated. But I think I'm going to try the lead, because lead, to me, we haven't worked with lead before. So I'm going to say, let's get rid of him first. So what's the first thing that I would do? I look at my numbers and I think this is a 1, this is a 3. What can I take this number times to get 3? And you would tell me 3. So I'm going to go through here. 3 times 4 is 12. 3 times 12 is 36. We're going to need our calculator, aren't we? And 3 times 1 is 3. Wow. Am I even close? No, I am not. Oh, wow. Ha, 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 ha. Okay, how about our P's? Okay, because I don't want to mess. This has like 2 things in it. Let's go to this one. How about the phosphorus? I have 4 here and I have 1 here. So what could I take at times to get 4? You said 4, you're correct. So 4 times 3 is 12. 4 times 12 is 48. 4 times 1 is 4, and 4 times 4 is 16. Am I any closer? No. So I have 12 and 12 here and 2 there. 12 and 12 is what? 24. What would I have to take times 2 to get 24? And you would say 12. So let's see what happens here. 12 times 2 is 24. 12 times 4 is 48. 12 times 3 is 36. So nitrogen, I have 24 on this side because of the two 12s. Oh, that matches good. Hydrogen, 48. I got 48 here. Phosphorus and phosphorus both have 4. On this side, I have a 16 and 36. And added up together would be 52. Looks the same thing over here. And I have 3 leads on either side. Again, if you would want to, you can place a 1 in here to show that that didn't need a different coefficient. The coefficient is still 1. So again, you can get some really big numbers. So be aware of that, and that's okay. So now you can try practicing on your own assignment.